Three numbers sit at the center of this paper: 17,393, 3,885, 10,309. They are the published population estimates for wild horses, brumbies, in Kosciuszko National Park across 3 consecutive years. Between the first and the second, a decline of nearly 80%. Between the second and the third, an increase of more than 160%. This paper, Reconcile one year with the next, examines what those numbers can and cannot tell us, and asks whether they can carry the weight of the decision resting on them, because the decision is not small. Population estimates in Kosciuszko are used to justify management intervention, including lethal control. Its argument is scientific, ethical, and cultural, and it moves through a single patient sequence. Field observations, detection, sampling, model, estimate, uncertainty, reconciliation, independent reproduction, verification, and only then decision. Its position is stated plainly at the outset: verify before irreversible action. This paper does not pretend to be neutral, and it says so in its opening pages. It supports the brumbies. That is not a hidden assumption buried in the framing. It is an explicit advocacy position, declared before a single calculation is made. The paper opposes trapping for the purpose of killing. It opposes ground shooting. It opposes aerial shooting. It opposes lethal population control in every form it currently takes. And yet, having declared its position, the paper holds itself to a deliberately rigorous standard for a simple reason. Advocacy is strongest when its factual propositions can withstand independent scrutiny. It is that the evidentiary standard should be stronger before an irreversible intervention is authorized. When the proposed action cannot be undone, the evidence supporting it must be held to a higher bar. That is the position. Everything that follows is the case for it. Here is the sequence at the heart of the matter. In 2023, the published estimate was 17,393 horses. 1 year later, 3,885. From 2023 to 2024, the published point estimate fell by 13,508 horses. That is a decline of approximately 77.7% in a single year. Then, in 2025, the published estimate rose to 10,309. From 2024 to 2025, the point estimate increased by 6,424 horses. That is a rise of approximately 165.4%. The paper is careful about what these movements do and do not establish. Changes of this magnitude do not automatically prove that any estimate is erroneous. Wild populations can move, survey methods can change, conditions can differ from year to year. But changes of this magnitude do require examination. A number that falls by more than 3/4 and then more than doubles is asking a question, and the question deserves an answer before anything irreversible is done on its authority. Begin with the 2023 estimate, 17,393 horses. The evidence examined in the paper records 6,393 reported removals. Subtract one from the other, and 11,000 remain. That figure is an arithmetic residual, not a claim about the actual 2024 population. Real populations have births, deaths, and movement, because the reported 2024 estimate was 3,885. 11,000 minus 3,885 leaves 7,115 horses unaccounted for between the two published numbers. Instead, it names the figure precisely, a reconciliation residual, requiring scientific attribution. What could account for it? Births, natural deaths, immigration into the park, emigration out of it, additional removals, survey coverage, detection probability, sampling variation, methodological changes, model specification, observation error, statistical uncertainty. Any of these, in combination, might explain the gap. Some of them concern the horses, others concern only the survey. The appropriate scientific response is not to assume which of them did. It is to quantify and reconcile those components wherever the evidence allows. The second numerical problem runs in the opposite direction. From 3,885 in 2024, the published estimate rose to 10,309 in 2025. The difference is 6,424 horses. As a proportion, that is an increase of approximately 165.4% in 12 months. The calculation does not establish that 6,424 additional animals physically appeared in Kosciuszko National Park. It establishes that the published point estimate changed by that magnitude. Those are different claims, and they call for different kinds of evidence. That is not a criticism of the estimate. It is a statement of what estimates are. The appropriate scientific question is therefore not, where did the horses come from? It is this: what combination of biological population processes and observation processes explains the transition from 3,885 to 10,309? Perhaps the population grew. Perhaps the survey saw more of what was already there. Perhaps both. Until the components are separated, the number cannot say. It is not a head count. Wildlife abundance estimation is an inferential process, and it moves through a chain: field observations, then detection, then sampling, then a statistical model, then an estimate, and finally its uncertainty. An observed count is not automatically equivalent to the underlying population. Distance sampling methods exist precisely because detection is imperfect. An animal can stand within the survey area, alive and present, and never be seen. In steep, timbered country, that is not a rare event. It is the expected condition of the survey. So observed animals are not necessarily all the animals present, and an estimated population is not a direct census. Detection varies. It varies with terrain and vegetation, with weather, with the observer, with the animal's behavior and group structure, with the survey platform, the timing, and the conditions on the day. If detection changes between years, an apparent change in abundance may contain an observation process component. Part of the movement in the number may reflect a change in how well the survey saw the horses, rather than an equivalent biological change in the horses themselves. 2 years, 2 numbers, and no guarantee they were measured with the same eyes. Sampling determines which portions of a population are observed at all. A scientifically transparent survey should identify its boundaries, its sampling frame and sampling units, its effort and intensity, its timing, its coverage, its exclusions, and its procedures for extrapolating from what was observed to the wider population. Change any of these between years, and the comparability of the estimates changes with them. A survey that flies different lines, in a different season, over different ground, is measuring a different thing. Comparing 2 population estimates, therefore, requires examination of how both estimates were generated. The estimated population in any year is a function of 4 things: the observed data, the sampling design, the detection process, and the model's parameters and assumptions. The statistical model is itself part of the evidence. A published population number, without an adequate explanation of the model that produced it, cannot be completely evaluated. And every estimate carries uncertainty, of several kinds at once: sampling uncertainty, detection uncertainty, parameter uncertainty, process uncertainty, observation error, model uncertainty, and uncertainty arising from the assumptions themselves. Reconcile one year with the next. Annual estimates are not isolated facts. They are observations of a temporally connected population system. What explains the transition from one estimate to the next? The first is a biological one. Next year's population equals this year's plus births, minus deaths, plus immigration minus emigration minus removals plus natural variation. That describes the animals. The second is an observation equation. What the survey records depends on the true population, the detection process, and the sampling design, plus observation error. That describes the measurement. The population process and the observation process are not the same thing, and a change in a published estimate can reflect either, or both, genuine population change, altered detection, changed sampling, methodological change, or some combination of these. Reconciliation means accounting for births, deaths, removals, movement, detection, sampling, methodological change, and uncertainty year on year. The objective is not to force two numbers artificially to agree. The objective is to explain their relationship. The second central principle follows directly. Allow independent experts to reproduce the result. Reproducibility is a cornerstone of credible quantitative science. A qualified independent researcher should be capable of examining the analytical chain and determining whether a published estimate genuinely follows from the underlying data, the survey design, the detection assumptions, the statistical model, its parameters, the uncertainty procedures, and the final calculations. It means being able to reconstruct and test the analytical result within its stated methodology and its stated uncertainty. If the result cannot be reproduced, the deficiency lies with the evidence, not with the reviewer. And where legally and ethically appropriate, independent examination should reach the whole of the chain: survey methodology, dates and boundaries, sampling design and effort, the observations themselves, detection assumptions and detection models, the statistical models and their parameters, confidence intervals and uncertainty calculations, the treatment of missing data and repeat observations, movement assumptions, removal records, methodological changes, data processing procedures, analytical code where practicable, and the final calculations. None of this is an accusation. It is the ordinary discipline of quantitative science, applied to a case where the consequences of error happen to be permanent. Consider what can be corrected. An error identified before intervention can be corrected. A population estimate can be corrected. A statistical model can be corrected. A spreadsheet can be corrected. A report can be corrected. A confidence interval can be recalculated. Every artifact of the analysis is revisable. That is what makes it science. But an error identified after intervention cannot undo the intervention's physical consequences. Once a Brumby has been killed, no subsequent correction to a population estimate can bring that Brumby back. An asymmetry between statistical error, which is reversible, and physical harm, which is not. When the two sit on either side of a decision, they should not be weighed as equals. That asymmetry should affect the evidentiary threshold applied before intervention. It asks that the burden of proof match the permanence of the act. The greater the irreversibility of the action, the stronger the demonstration required to justify it. Verification after the fact is not verification at all. It is an autopsy. A population model can estimate abundance. It can estimate trends, uncertainty, demographic parameters, and possible population trajectories. But a model cannot independently determine cultural authority. It cannot determine cultural obligation, spiritual meaning, or cultural responsibility. It cannot determine whether killing is culturally acceptable. Those are not statistical questions, and no confidence interval will answer them. They belong to people, to communities, and to the histories that bind them to this country. Different forms of knowledge address different questions, and the paper holds space for indigenous knowledge and for cultural responsibilities concerning country, obligations to living systems, to animal relationships, to place, to history, and to appropriate conduct. The paper's position is that cultural assessment belongs inside the decision process, not appended to it, and that authority over questions of this kind cannot be delegated to a model that was never built to answer them. Numbers can inform the decision. They cannot own it. All of this operational, The paper sets out a formal independent audit in 11 stages. Stage 1. The data audit. Identify the data sets used for each population estimate. Stage 2. The field audit. Determine where, when, and how the observations were collected. Stage 3. The detection audit. Determine how imperfect detection was estimated and incorporated. Stage 4. The sampling audit. Determine whether the sampling design actually supports the population inference. Stage 5. The model audit. Reconstruct the statistical model itself. Stage 6. The uncertainty audit. Quantify sampling, observation, parameter, process, and model uncertainty. Stage 7. Temporal reconciliation. Reconcile each annual estimate with the estimate that preceded it. Stage 8. Independent reproduction. Allow qualified independent experts to reproduce the analysis. Stage 9. Sensitivity analysis. Test reasonable alternative assumptions and model specifications and see whether the conclusions hold. Stage 10. Cultural assessment. Assess the proposed intervention against relevant cultural beliefs, obligations, and authority. And Stage 11. The decision audit. Determine whether the proposed management action remains justified after all the evidence and all the uncertainty have been considered. 11 stages, in sequence, each one answerable. Nothing in the framework is exotic. It is simply the full chain of custody for a number, followed from the field to the decision it is asked to justify. The critical management question should not simply be, what is the population estimate? It should be, would the proposed management decision remain justified across the credible uncertainty surrounding that estimate? A decision that depends on a single uncertain point estimate is less robust than one that remains justified across a credible range of estimates. And this principle matters most when the proposed consequence is irreversible. With that established, the paper's policy recommendation is unequivocal, and it is stated without qualification. No trapping, no ground shooting, no aerial shooting, no lethal control. The paper advocates the protection of brumbies, and where genuine management questions arise, it sets out the preferred approach in their place. Rigorous monitoring, transparent evidence, independent scientific review, non-lethal management, habitat and landscape assessment, cultural assessment, ongoing evaluation, and the protection of the animals from lethal intervention. It is a demand that management be built on evidence that has been demonstrated, reconciled, and independently reproduced, and that while that standard remains unmet, the response that cannot be reversed is the one response taken off the table. In 2023, 17,393. In 2024, 3,885. In 2025, 10,309. Reported removals, 6,393. 17,393 minus the removals leaves 11,000. Set against the 2024 estimate, that leaves a reconciliation residual of 7,115 horses, still requiring explanation. The following year, the estimate rose by 6,424, 165.4%. The question is not whether a number has been published. The harder question is whether the number can be demonstrated, reconciled, and independently reproduced. There is a proper sequence: field observations, detection, sampling, model, estimate, uncertainty, reconcile, independently reproduce, verify, and then, only then, decide. And there is a sequence that should not occur: estimate, intervene, kill, correct the estimate later. The first sequence treats killing as a conclusion. The second treats it as a working assumption. A model can be corrected. A calculation can be corrected. A population estimate can be revised. A brumbie cannot. Reconcile one year with the next. Allow independent experts to reproduce the result. Verify the science with hard evidence. protect the brumbies.